So you've got 25, 18 plus. We should get started with the next session. As Louis just announced, vote for the your favorite particle and or astroparticle posters before 7 o'clock tonight. And we're going to start with Tillman telling us about unfolding and ML and more.
And more, yes. Thank you for having me, and a special thank you for Luis for bringing me in here last minute. So I'll talk a little bit about unfolding after we already gave you a very comprehensive and convincing case for unfolding. Here's a bunch of slides which given that it's late, I just run through them. So I think the key feature of the why LHC theory is doing machine learning is that unlike in other fields, we are in charge, as theorists are in charge of a fair fraction of the simulation chain that starts from quantum field theory. And then he does all kind of stuff, and including detector simulation, which then the experimentalists are in charge of. And the one thing that's important to me always is to emphasize that it's we do first principle simulations and not modeling. And then I noticed that machine learning Paul called modeling first principle simulations, but it's so it's first principles what we are doing. And Jonas already showed you this little graph where in the simulation chain machine learning can have an impact, and the subtle message of that graph is everywhere. It will have an impact everywhere. And why do we have to do that? And that's because in view of the high lumen LHC, we have to think how we do an optimal inference with 10 times the data that we have at LHC run 3. And that you take the square of that, and that means 10 times more data means 3 times statistical improvement. And you can think of predicting space-based distributions all over phase space to a per mil or something. If you don't do a per mil, the two-loop calculators will tell you you're useless. And then when you think about theorists again, SBI, as we heard from Wojciech, SBI S stands for simulation, and that's what theorists do. So this means theorists and experimentalists, we have to work them together on these SBI methods. And there's just from my group, Giovanni had a poster on some SBI methods, and then Ramon will also talk about event generation and how machine learning is used for that. So the key word there is madness. And these are simulations, right? These are simulations. So obviously this is going to be related to the development of generative AI. And generative AI is absolutely brilliant these days because there's a revolution going on that's has nothing to do with us. I mean, we can just ride this wave essentially for free, and that's brilliant. So what we want to do is we really want to learn phase-space densities in whatever phase space that we are thinking about here. And in the lower part, you can see the different phase spaces we are thinking, after hard scattering, then including decays or QCD radiation, fragmentation after detector effects, recall level, whatever you want to learn. These are all phase spaces, right? And Jonas told you already that we know a lot about these phase spaces, so I think consider them as effectively interpretable. I mean, we trained students for years to consider phase space interpretable. And this is, by the way, a figure from Jonas that's supposed to illustrate that in the last couple of years. So I've been doing this since Ramon Winterhalter started his PhD, we're doing generative AI. It was 2017 or something like that. And so variational autoencoders were already pretty useless when we actually started. So we never touched those, but we did generate GANs, which I still think are the coolest networks around. Then we moved relatively fast to normalizing flows on /diffusion networks, which work extremely well if your phase space is actually not that big. I mean, like, we're talking like anything between like 20 and a couple hundred dimensions, depending on what phase space you're looking for, like, at the parton level versus at the, like, particle level with pions and kaons and stuff. And they're super stable in training. And then more recently, we have tried like, transformer models, like, I'm very proud that we wrote the first paper with the name JetGPT in the title. Gregor said he was jealous of that. And then more recently, we have done these equivariant networks. And as I said, like we heard about that, they are basically the future. What really is the future, though, is like, once you're at a certain level of technical sophistication, is to, like, combine these things. Like, for instance, to use for simple density estimation, like, a flow model or like, diffusion model. But if you want to describe combinatorics as part of that, and the combinatorics means non-local interactions, you like throw in a bunch of, like, transformer layers because they are really good at, like, learning these kind of correlations. So this is, like, what the technique is driving us. Here's like the slide that Gregor said he wanted to show, and he couldn't show it because he didn't have it anymore. So this is the classifier test, and this is like, also what we heard from Oishik today and from Vinny. So what we do is we typically, when we want to see how good a generative network is in LHC physics, we train a classifier. Like, classifiers are easy to train, much easier than generative networks, and we train a classifier between training data and generated data and see if there's any difference. And then to make it a little bit more like easier to interpretable, we compute this like re-weighting term, W, which is really just D divided by 1 minus D. You could also look at D, but the re-weighting means, it's the correction weight that you learn. And then we make these kind of distributions. And you see here, these are like, 3 models. It doesn't matter like, what they are. These are all 3 unfolding models that we also saw in Vinny's talk. And you see how from red to green to blue, this becomes much more narrow. And now we have an incredibly precise network. I mean, we literally cannot tell apart the training data from the generated data. I mean, the peak is very strong. The other thing is, like, when you look at these distributions, you see tails, and tails is like, where stuff happens that you don't want to happen. For instance, you generate regions and phase space that you shouldn't be there. So that means you need to weigh them down, which means you get a tail at very small W's. Or you like miss a feature, which means you have to recreate it, which means you'll have a tail with large W's, right? But Louis, this is just like, a tool to analyze our networks. I don't care at this stage how, like, how precise even it doesn't. As long as it tells me the weaknesses of my model, I'm happy, right? I mean, this is like, the main reason why we're using those. Okay, and then like, here comes the question that like you always get asked from your, like, university presidents, like, okay, it's all fine, you're doing machine learning. Where does machine learning transform your field of research? Right? Like, I know all of us have heard that question, and we all have our answer. And my favorite answer is LHC physics. That's unfolding, as you learned from Vinny. And there's 3 reasons for that. Actually, Oishik and Vinny. So the first one is the number of searches we're doing. We do not want to, like, simulate the entire forward simulation chain for every bloody signal, every like a model builder comes up with. I mean, this is just a waste of time. So like, if you want to test a large number of different models, like unfold stuff, like the data to a level where simulations for the signal are cheap. So then you can test your models, right? For cheap, and you don't have to, like, spend that much GPU time. The second one is optimal analysis. Like, some of the theory predictions, they get better with time, and it's not guaranteed that all of these theory predictions are always in MATLAB or Pythia or Sherpa, right? Some of these theory predictions at 3-loop QCD are not. So if you want to include them, you have to, like, compare at a level where, like, that group, like, gives you these predictions, and that might be an unfolding level at some level, like, hard scattering or whatever you do. So, like, optimal analysis might require unfolding. And then publication, right? Everybody says it's pointless and, amateurs can't deal with LHC data. And that is actually correct, except for Jesse. He managed, he's the only person I know who managed. In truth, it's not that hard. It's just the detector simulations are super hard, but the detector simulations is not where I expect any new physics anyhow. So, like, unfold those and let the amateurs or, like, whatever, deal with, like, the data at a simpler level. And the simpler level means unfolding to me. So these are 3 cases why I think LHC should publish their data through unfolding. So here is, like, just my favorite graphic, like, how unfolding works. Unfolding is just a story of 2 conditional probabilities, right? Forward simulation here to the left you see like, you know, on the simulation chain, we have xpart could be xparticle, xparton, pick your favorite phase space. And a RICO is the RICO level, right? Like, you know, this is what we observe in the, like, you know, the detector tools, analysis tools. And the forward simulation is basically you turn a particle or a parton level event into a RICO level event through a conditional probability. And that conditional probability is called Geon4, for instance, right? It's encoded there. Or in fast versions of that. And unfolding is the opposite. Like, you know, you basically take your data, X RICO, and you somehow from simulations or else, like you learn the other way around, the other condition probability, apply that, and you get the unfolded data. So like really, these are just two conditional probabilities. And now inverting stuff, there's an information loss, but hey, everything in particle physics is anyhow how stochastic, if not quantum, as we learned from Oishik, so that'll be fine. The question is, can we do this well? It's not a question, can we do this in principle? People have done this for a long time. Can we do this well? So here's my slide on omnifold, but there was a lot of like talk about omnifold. So omnifold, what they're doing is actually they have they calculate classifier weights at the same phase spaces, RICO, like between simulated and data, and they push and pull them back and forth. And then there's a magic step 2. And then you get like, you know, an unfolded distribution at the parton level that represents the data. What's interesting is that omnifold in this my little square uses all directions except for the one that defines it. So like, you know, it is a beautiful, like, you know, like way to like, you know, get where you want to go, but like, you know, going one corner here over, right? In my little thing. This is not at all biased, obviously. And so what we did, like, you know, we've been doing this for like about as long as omnifold exists. We're trying to, like, you know, basically like learn the conditional probability on the right-hand side. The reason why we do this is because I'm a simulation guy, so I know how to do the forward simulations, you know, the left, like, you know, up from top to bottom. This I've been doing for like, I don't know how many decades. So like, you know, if I told you it's symmetric, I can also do the inverse one. And this is really the conditional probability. And then also, Vinny showed this, then you have to make sure that your simulated RICO distribution that you use for training and the data RICO distribution, they actually correspond to each other. And that is the second reweighting step that like, you know, Anya Butter and like, you know, Bogdan and Monica Dunford like, you know, put in. And that is absolutely crucial. So this to make sure this correspondence solved. But aside from that, it's really just conditional probability learning. And these are generative networks. Conditional probabilities what generative networks are good for. And here, these like, you know, these are like, you know, it's an example from a paper we wrote that also Vinny showed, where the Californians and us and everybody, and we compared all kinds of different methods. And what I'm very proud of this is like, these are the like basically the migration plots. So like, you know, there is the RICO to parton level like migration here. This is like, you know, just like a calibration curve if you think about it. To the left, this is the forward simulation chain. This is like, you know, the physics, how like the detector works for tau 2-1, which is uncertainties, like ask Jesse about it. And then in the middle, this one is an unfolding method, direct diffusion, which works for distributions, but it actually doesn't respect the physics, right? And it has a different map. And the right-hand side, you see like, you know, these conditional probability methods, they reproduce the physics optimal transfer from like, you know, one data set to the other. The one in the middle, by the way, if you just want to like, you know, unfold a bunch of distribution, it might be super useful and efficient to do this because you might not even need paired data to train it. But like, you know, for us, like our gold standard is I want to learn the physics forward simulation correlation. Okay, and now this like goes back to Olaf, like, you know, like a while back, I like, you know, gave this talk and it's my story. I asked those guys, okay, what's the kind of problem that you would never solve with and want to touch with unfolding? And then Olaf and friends said, yeah, like, you know, on shell particles. It's really stupid to try to do this. You're gonna be miserable, I think you said. And so we decided we want to be miserable. And so we went for that application. So, and here's the complication in that, and that's the model dependence. So in the RICO level, and now on the simulated part, you have the simulated top mass value, MS I call it, right? Now in the data, you have MD, that's the top mass in the data. But the learned condition probability you learn on the simulated data set, which means that one P model depends on MS, which means if you apply that to the two data, MD, you get a double dependence up there, right? And that gives you all kinds of bias and hell, right? It's really, really hard get rid of this. So the technical question that we did here with like, with the CMS group in Hamburg is like, can we deal with that? And yes, and what we said, I can weaken the bias by training on an MS range. I can strengthen the data with some tricks. And then I get this kind of results. So what I get is I have the triple jet, so that's the top mass. I get the generated, which is black. I get the reconstructed blue. I want to get back the generated. So I get the unfolded red one, and the ratio between unfolded and generated, you see, is the red line. You're talking 5% distribution around the peak, right? So that we actually learn that distribution around the peak. So this is 4-dimensional unfolding. You can measure top mass in that. If you want to measure the top mass and calibrate it, better make sure you also get the W mass route. Here you go. W mass, beautiful, no problem. It's actually easier than top mass because it's a 2-particle, not a 3-particle correlator. And then you can say, here, like, this is for Jesse. That's, that's the iFile logo turned around. This is the correlation between, like, 2 of these masses, and it shows you that we can do the same thing. We can publish this in 12 dimensions, right? So we can do this unfolding, and this is generated unfolding. By the way, this is one of the problems that doesn't work for omnifold, I believe, because with top mass peaks, these weights might become very big, and it's numerically a pain, at least. Actually, I'm not saying it won't work, but it's painful. But
we need to solve that problem. Apparently, they need to solve that problem
with our paper together.
No, with the one that has this new ability to find nuisances.
Oh, okay.
You can treat the top mass.
Yeah, that is probably the same because you can treat those as nuisances. But let me just spend a few minutes on something else, because on the other thing, and that is learn uncertainties. I showed you some unpublished CMS simulation, by the way, And to be fair, I also want to show you something that's unpublished in Atlas, because I want to be fair to everybody. So here, this is basic generative networks. Bayesian generative networks is my hobby, because it's like basically generating stuff with Bayesian networks with well-defined loss functions and an error bar on the learned density. And here, this is a nice little example, because you have a density you learn. It is the lower one here is the density in the 2-dimensional plane. It doesn't matter what it is. What's important is there's a structure in the uncertainty, and that tells you something about how the network has learned stuff. And this is INNs, so normalizing flows, and DDPMs, diffusion models, look the same. If you plot the same thing, the sigma here, you plot this for conditional flow matching, or for transformers, they look different. So why I like these the Bayesian networks is because they tell you something how the network learns the functions. Also, by the way, we had that discussion earlier. It's super well defined, like Bayesian networks, because this is actually Bayesian inference encoded in networks. So, but also they give you the error bars. So here's my Atlas results. What we wanted to do is together with our old friend Peter Loch, we want to calibrate topo clusters. And this is really just learning a scalar field over 15-dimensional feature space. It's not that hard, or phase space, right? So we learn to learn that, and that is the calibration function is the recorded electromagnetic energy over the deposited electromagnetic energy, as you know this from simulations. Right, and I want to learn this, and you can look at Nina's poster how we do this with uncertainties, and then we can use Bayesian neural networks or repulsive ensembles. Both of them, by the way, should give you a proper posterior estimation. Normal ensembles will not. And you want to check this. What do? You check the pull distribution on the data, and the pull distribution should be roughly Gaussian, if if it's a stochastic data set, roughly Gaussian with a width of 1, right, plus minus 1. And you see, both of these methods, green and blue, give us, well, they have a tail to the left, because nothing in life is really ever Gaussian, but they have a tail to the left. Okay, so this is consistent. This is essentially showing that the uncertainties are calibrated. But because Jesse was talking about interpretability, what can I do with that? I can, for instance, plot the left figure, and I'll plot the uncertainty, and I see something funny is going on at sigma around 10. I have a whole lot of topo clusters which come with a very large uncertainty. And you wonder, why the hell is this? And of course, you look and you study your network, and all is fine, until Peter Loch, our friend, the calorimeter guy, says, wait, let me look at those things. And he makes the right figure. And, it turns out that not all parts of the Atlas detector are equal. Some of them are just not as good at measuring energies, because, there's different parts of, and there's this wheel, and then there's in between some space. And this is where they all sit. So we have just learned, we have taken the Atlas simulation, we have trained a Bayesian network on jet calibration, and we have learned where the Atlas detector has holes. Now, I mean, Atlas probably knew that before, but it's still a nice example, how you learn something from training. neural networks properly. In case for the others people who don't know that the detector has holes. Okay, we're done. Yeah. This is like, developing ML. I mean, the reason why we do this, we want to do the best science. And like, you pick your science. But you want to be a scientist. We want to use, I don't want to do the best ML. I want to do the best science with it. And like, I always say that, like, if I'm in front of a bunch of ML skeptics, I would say it's just another numerical tool for numerical field. But I said this as IFI. Of course, that's not true, right? I mean, it's a transformative tool, like, that allows you to do a lot of things that you couldn't do before. Like, and this is what makes it so interesting. The other thing is also that it's a new common language. We're sitting here with particle physicists and astroparticle physicists, and like, we couldn't actually discuss Higgs discovery or like SMEF stuff, like, what you used to do before I did, right? But I mean, I need machine learning to talk to you people. Also, I don't have to pay for it. It's driven by extra money. Like, as the companies pay for it, like, whatever medical grants pay for it, everybody pays for it except for me. And then there's like, you have to watch one of these match Mortz's talks about the 10,000 Einsteins. So it enables people to, we are all going to be Einsteins at the end of the day, is what Matt says. And he's right. I'm not. The young people are, we have a whole generation of Einsteins, the golden generation. And there, I mean, we heard this earlier. There's 3 ways you can use machine learning. The first one is to improve established tools. I mean, this is what Atlas and CMS live from. Right? Like, this is what they do for a living, except it's also super boring, right? I mean, you do something better than everybody before. And the only thing is, like, that happens is that people who did it before hate you afterwards, right? So it's not that exciting. What is exciting is you develop new tools for exciting tasks that people couldn't do as well before. And that, I believe, like, unfolding is something that we couldn't do as well. And, the CMS group doing this project with us is actually an unfolding group. I mean, they know how to unfold, and they came to us and they can we do this better? And we love each other now because, we unfold like they want to, and we can do it better, right? And sometimes there's completely new ideas. And of course, we're all looking for those. But you're young, you do that. Thank you. Brilliant.
All right, very good. And we have time for questions. Second row. Okay.
Yeah, Tilman, yes, you about this top thing. But I mean, if the top resonance or this hadronic jet mass, top jet mass would be really a delta function, then you couldn't unfold it. I mean, we had this unfolding workshop, and Michael Schmeling said, unfolding is not deblurring because there's some frequency limit, right? I mean, you can't unfold below the detector resolution. So I think that what you exploit is that the top quark still has some kind of not so small finite widths here, and then I mean the resolution is factor 2 broader, so that's still solvable. But yes, right. I mean,
so I would argue that classical unfolding methods, you could use classical unfolding methods, but their resolution is much worse than detectors' resolution, so that you lose. And so the question is, can we bring the precision, like, the resolution of unfolding to the detector? There's no, you cannot invent stuff.
No. Yeah.
Hi, yes. So you talked about there's a sort of classifier way of doing unfolding, and then there's the generative way of doing unfolding.
Yes.
Typically, when you're training these generative models, you would do something like a classifier guidance term, training on the output of your generative model compared to what you want, and using that, or you can use that.
You could.
Is that it? So I mean, all I'm kind of saying is there actually, are these two things compatible?
We don't. So when we train our generative models, we train on the joint distributions of the 2 phase spaces simulated, and typically there is no classifier involved in that training. We used to in the old days when the generative models weren't good enough, and you needed this extra step, or against have the classifier by definition. The current, what we call track FM, so like the traditional flow matching with attention layers is so good here. I mean, you can run a classifier on this in addition if you want, but like, here we use a classifier really only to check how good your models are. But this is a very recent development. I mean, so as I said, we are sailing the wave of generative AI revolution, smart people doing good stuff for us.
I mean, maybe it's more a question to Omnifold then. Could you include the generative model to, if high weights are a problem in a classifier approach, a generative model can soften that distribution for you, right? Or it sounds like that's what you're saying it does already.
You're writing one paper after the other with Ben Nachman's group, right? On like, so like, we are not fighting each other. If there's ever like, like the idea is always there's like, for your unfolding problem, pick your method. So for instance, I think Ben is convinced that this reweighting that like, Anya and friends for the generative model they came up with is literally the same as this Omnifold step, the like iterative, Bayesian iterative stuff. So we're talking to each other all the time. We're currently with Vinny developing another way of generative unfolding, which is not yet different. So the idea is that pick the model that works for your problem, or the approach that works for your problem. And if you find that a combination works for your problem, please do that. I have no, like, yeah. But unfold and publish the data, please.
Yeah, thanks for a nice talk. So I have a question. So like, would you say one conditional distribution is easier to learn than the other? So the folding versus the unfolding?
So, I mean, unless your detectors will crap and you miss a lot of information and you basically a lot of one of the like distribution actually is it involves a lot of noise, which is not the case for a typical energy detector. No, I would think it's probably
so then I guess my question is somehow okay. Then I mean, by the same token that you can give everybody a tool to unfold, you can give everybody a tool to fold.
yes.
Right. And so everybody, so if the entire motivation of unfolding is that it's expensive to run the folding step or annoying to run the folding step, you can somehow simplify that to just like an afterburner neural network evaluation or generative neural network evaluation. So what does, I mean, does that somehow touch the unfolding story at all if everybody can fold?
No, I think you're right. So like, the number, so what the forward thing that is essentially a fast detector, ML fast detector simulation, right? You could probably do that. I mean, people are working on this. We are also working on this. Everybody's working on that. So you could do that. The problem is that the data format that comes out for publication is still much more painful than than before detectors, because I mean there's essentially one physics step. In other words, as a theory group, I can run MATLAB or Madness and I can go to pattern level or including decays or something and do my analysis there and look for like alps, whatever, right? I mean, or Z primes. Whereas if I had to understand the data at the detector level, just the data format, right? It's much harder. I think like if you want to publish the data. So in the experiment you can choose, but if you want to publish the data, you broaden your user base. I think the unfolding has an advantage.
We're out of time, so we should thank Tillman again. Up next. So up next is Will, who's going to tell us about linear simulation-based inference.
Right. Oh, there we go. Okay, so I'll begin by pointing out some point. I get that to work. Okay, so from Jesse's talk, he finished with the rather provocative statement when asked, what is the most underused machine learning technique in physics? His answer is only half jokingly linear regression. And that's basically what this talk is on. This idea being that actually you can get a very long way with linear regression without neural networks in the case of simulation-based inference. Simulation-based inference has been mentioned quite a lot. I'm sure there'll be, and there's even some more talks later in the day, but Ben, Max, Andre, and Josh on Monday, and Ashik today, and I think possibly even more since I sort of was making these slides over the course of the day. in terms of who's been working on this, the main person that's been driving this for the past sort of half year or so is Nicholas, who's an MSci student who'll be looking for PhDs this round, so I can thoroughly recommend him, and David, a postdoc who works with me, and Thomas, who's now left us. I'll also point out that this is not that new in that a lot of this stuff is well known to those who know such things, that these are sort of methods that are quite well established. And certainly Florent Leclerc in Selfie incorporates some of these ideas. Some of these ideas are also in Moped from Alan's work. And there was a paper in April of this year by Hagstrom that is very similar to this. And that will teach me for sitting on this for about 18 months and not publishing it. But I will sort of present some of these results now, and just as an idea for why this is powerful and why this is useful. So you've seen a version of this plot already from Ben. I will do it, my version of it, because A, it's a little bit more snazzy, and B, this uses the LSBI package that I'm talking about in this version. So if you want to see the source code that makes this, you can go to that link at the bottom, and that will give you the tech and the Python that allows you to make these kind of plots if you want to. Okay, so as we've established already in this meeting, if you don't know the likelihood, but you have a forward model, the forward model implicitly samples from the joint distribution. So to be clear, we'll say that if you know theta, even if you don't know what that green likelihood is, so on the x-axis we've got theta, this is typically of order a few parameters, so that might be 6 if it's cosmology, it might be 30 if it's cosmology with nuisance parameters, and it might be 30 if it's the standard model of particle physics, and you've got data, which will usually be about the same number of parameters if it's massively compressed, or a lot more than the number of parameters if you're working in an uncompressed space. Although you might not know the likelihood, if you can sample from a generative process, that means you can effectively, over time, build up simulations in this theta d space. So you can see here, I've drawn a line sort of conditioning on theta vertically, and a purple dot saying I've drawn a new point in the theta d space. If we define some range, some measure on parameter space, or a prior if you're feeling Bayesian, and then draw from theta and then from d sequentially, you find that you can build up samples in this space and eventually get to a set of samples from the joint distribution. So this is the core idea behind simulation-based inference, which used to be called likelihood for inference, but because that sounds like snake oil, we've sort of moved to this new way of thinking about things. The principle fundamentally, which is the core theory, is that if you have a generative process, you can sample from the joint. Where the joint is the probability of everything. It's P of theta comma d. It's also sometimes known as the unnormalized distribution, the thing that you feed into your Hamiltonian Monte Carlo. But it'd be much better if you just called it the joint, because that's what it is. So the key idea behind simulation-based inference is because we can sample from the joint distribution, and therefore what we want to try and do is to turn those samples into some representation of that, i.e. to learn the implicit joint distribution, or equivalently, the posterior and the evidence, or the likelihood, or just learning the joint directly. And at the moment, that is achieved using, rather the state of the art is achieved using neural networks, because there's been a recent flourishing of work here, because neural networks have become sufficiently expressive to be able to tackle this problem in of order 14 dimensions, which is kind of the gravitational wave side of things, or the things like that. We'll come on to, if we have time, how I think this might scale in the future. But for now, that's the core idea. Just to kind of finish this plot, if we then say we saw some observed data here, okay, you then slice across your representation that's now some either conditional neural density estimation, or sort of some other version of that, where you actually just sample from a likelihood that you've learned. And then once you condition that data, you pull out the posterior in the blue. So you see the prior in the orange and the posterior in the blue, because we've seen that. And if the data came down lower, we'd see we get a broader posterior, because the data is less constraining in this region. This data is less constraining the parameters. And of course, if it came at this midpoint, you might find you could get a bimodal posterior. This is nice because all of that is an exact plot. That's not me fiddling around with paint or something similar. That's the LSBI package producing those distributions exactly. So it's quite nice. You can make pictures of cats or things like that and have the conditional of a cat, or the marginal of a cat. Right. So that's the core idea behind it. Right. So why would we want to do linear simulation-based inference? as we've said, much of the drive recently has been because we've had a very, very strong set of neural network technology able to start tackling this directly. So I'd say, first of all, it's pedagogically very helpful. It's nice to separate out simulation-based inference from machine learning, because actually this is more general than machine learning. Just because we've been able to do this now does not mean that, you know, in 20 years' time, when we've moved on from GANs, as it was, Shields was saying, sort of 3 years ago, or diffusion models now, there'll be some next generation thing that may not even be called machine learning, but the simulation-based inference core of it might still be there. So it's nice to separate those two out. It's also quite practically useful because these things that one can build have known ground truth answers. So you can basically check that your super duper machine learning method is giving the right answer if you try it out on one of these linear or mixture models that have direct, exact evidence answers or are correctly normalized. And it's also pragmatically useful. I found that in practice, this actually is competitive with neural approaches in terms of their accuracy. And because it's all linear, it is more interpretable if you're used to thinking in these ways. So let's go through a little bit of how this is. So this is the maths slide and the next one. This hopefully shouldn't be too awful, and it's more of a reference if you want to sort of download and look at after the fact. I don't know if there's any chalk, but we're not, no. Just do it this way. Okay, so we've got a generative model. Excellent. Right. So the way you should be thinking about this is you've got some data, D, of size D, which can be composed of a smaller vector of parameters of size n, and some larger matrix M, plus some vector M, plus and minus some larger covariance C. So that's the linear model where you have some vector parameters, which you have a transfer matrix M that transfers you into the data space. You then shift by little m, and that gives you D up to some covariance of scatter. So that's the kind of thing here. That's a physicist way of thinking about it, where I've written this kind of rather amorphous plus and minus root C. If you want to draw this as a normal distribution, you say D is distributed normally with mean M plus M theta and covariance C. We then define our simulations. We'll say there are k of those. So I'm good. These are the points from the previous plot here where we have these. So you should think about this here as being an n-dimensional vector, a d-dimensional vector, and there are k purple simulations in the joint space. And then from those k simulations, because we're working the linear space, we're going to be using things like this, where we define the simulation statistics, which this is just for convenience. This comes out of the derivation. Don't worry, I'm not going to derive this in front of you. But for now, we'll talk about the sample mean of theta, the sample mean of the data, the sample covariance of theta, the sample covariance of the data, and then the cross correlation between the two. Those are the things that just come out of that naturally, with this k-1 again coming out of the conjugate priors that I'm not going to do in front of you. Okay, so that's the key point. We've got data and theta, and we've got a linear generative model that is parameterized by M, M, and C. Little m and M for model basically is the mnemonic. So this is the hard bit, where what we want to do is we've got some simulations S, and we would like to learn what M, M, and C are from those simulations. The likelihood is just multiply the linear normal models underneath the hood, and it can be shown. So for those that haven't done this themselves, what this usually involves is you writing out pages and pages of matrix algebra that still inexplicably can't be done very well by Mathematica. Often for me, that involves, because I'm good enough with Vim, creating gigantic text files of things where I'm copying and pasting things until we get to this final distilled answer. And then you just sweep all that away, and in the paper say it can be shown. So this is what Ben Van Dijk calls the little red book. So if you don't know this, this is how you get some of these more esoteric matrix distributions, because we're trying to infer the unknowns M, M, and C of this model from simulations of D and theta. And in order to do that, because M is a matrix, you need to know a lot about matrix variate distributions. So what you get out of this is that, again, you don't need to follow this. This is for reference, but you find that M, little m, is normally distributed about something that involves the mean vectors. That kind of makes sense. Big M is matrix normally distributed, and a matrix normal distribution is a weird one that if you've seen it, you'll remember it, and if you haven't, I'm not going to go into it now, but that has two covariances. And then the covariance matrix C has an inverse Wishart distribution. For now, you don't need to follow any of that. All you need to know is that we can solve that problem exactly because it's linear, i.e. given some simulations S and a linear model parameterized by M, and C, you can exactly derive the posterior. Why would you want to do that? So first of all, as we shall see, for nonlinear problems, this is not a very good approximation at all. So this is only sort of reasonable when you do a little bit of extra. So my way of doing a little bit of extra is to work with sequential methods. So these are things that are not amortized, so they don't work for any data. They work for the data you've seen. So this is better. This is more cosmological, i.e. we've got one night sky, we want to extract as much information out of that as possible, but less appropriate for, say, gravitational waves where they want to do fast follow-up, or for particle physics where you want to do operate on lots and lots of new data. But for cosmology, we like sequential methods. And the idea here is that because it's a big ask to ask for a learned joint distribution across the whole theta data space, you instead concentrate your effort around the data you've seen. And one way to do that is to take the data you've seen and choose parameters theta that generate data near to the data you've seen. So instead of trying to cover the whole joint distribution, you cover a focus bit of that. And one natural choice of that is to use the posterior of your last guess. So I'm going to show you this graphically, so that rather than sort of following these words. So here's the same model as before. We've got theta on the x-axis and data on the y-axis, and the joint distribution as samples in purple dots. Same as before. Let's say that is our observed data D, and that blue thing is the posterior that we want to try and reconstruct, but we don't know because all we have are these simulations to work with. So in a sequential setting, first of all, you would fit a rubbish model using the linear simulation-based inference approach. So this here obviously does not capture that joint distribution. It's kind of, you can see that the non-linearity is dragging it so that it can only do a quite rubbish guess. So if when you try and derive a posterior from that, which we cheat, it's a very poor fit. So you can see the dashed blue line is the one that the linear model gives, and the solid blue line is the real answer that we're trying to get to. However, if you take the solid blue bit, so if you take the dashed blue bit and use that to generate new theta samples that are concentrated around where that data is, you end up getting those. So instead of populating the whole joint distribution, you populate a subset of the joint distribution, and that is then more targeted so that when you fit LSBI to that, it does a much better job. When you repeat that process several times, you find that you sequentially build up samples that are concentrated around the right area, and it turns out that around the observed data, a linear approximation is a pretty good one for getting this out. So that's the key core idea, that by working sequentially and focusing on the observed data, although the whole joint distribution is nonlinear, focusing on some region around the real data often is quite linear. Now, this is a problem where theta and data are both one-dimensional. So this looks quite easy, right? So let's do this on a harder problem that unfortunately I won't be able to visualize. Hopefully Firefox will work. If we think about it. So I need to really sort of hold my nerve here because it's a plot that I produced quite last minute, and it can take a bit of time to load, but if I press it more than once, it might go wrong. So what we're going to do now, what you should be seeing soon, is the same thing, but we upgrade theta to be a 6-dimensional parameter space and data to be a 2,500 dimensional parameter space. That 6 being the parameters of a lambda CDM cosmology. Okay, I held my nerve. I lost my nerve, but I didn't need to be doing that. Okay, fine. Here we have the 6 cosmological parameters on our triangle plot. Okay, so I'm not going to show you the 2,500 data vectors that are the CMB power spectrum. But this here is the prior, and the right answer, i.e. the answer that generated the problem I'm about to go, comes here, okay? We run simulation-based inference, linear simulation-based inference on this, and you find that at round 1, it gives you that green plot, which if we zoom into it, looks like that. And at round 2, if we run it again, it gives you that red plot, which if we zoom into it, this is where it starts to think, where we have an impromptu GIF given to us by Firefox. Here, you can now see that the red distribution was the last, and the red distribution was the last round we tried with the ground truth in this marked in black here. And then if we go again to the purple distribution, we find that we're now zooming in iteratively. So the thing you should be drawing from this is that whilst that 1D picture looked very pretty, this also works in a much more realistic scale problem. Now, this is not a real cosmological likelihood because real cosmological likelihoods are not written generatively. Although in principle we have the Planck likelihood, you can't use the Planck likelihood to generate data yet. So here, this is done for a cosmic variance limited temperature, only full sky CMB experiment with no foregrounds, i.e. quite an easy problem, but one which we know have a ground truth for. So that's how we're able to check it's getting the right answer. There is a slight bias here, but recent work has shown that when you marginalize over the M, and C, rather than just picking point estimates, that fixes that bias and it spreads it out. And more importantly, so that's the core idea, that basically this isn't just that 1+1 problem. This is a 6 + 2,500 problem without any compression. In the final minute or so, I will mention that the package itself should be relatively easy to install and use. It's from pip, it's continuously integrated in open source. I've spent a lot of time getting this right. So one of the things I'm more proud of is that it takes the scipy.stats multivariate normal that I'm sure we've all used many times at various points and vectorizes that. So obviously that is a vector distribution, but you might want to have that so there are multiple copies of it that usually would have to do a for loop around, but here it's kind of vectorized under it properly. It also equips them with marginalized and condition functions and plotting functionality, and then implements a linear model with prior, likely, posterior, and evidence methods that generate those things there. And also gives mixture model, which is how I've made these plots. And it's here if you want to have a look at it as in a beta form. In terms of things that are going next, we need to write up this paper. Nicholas is currently doing that with a soft deadline because his MPhil starts in October and a hard deadline because he wants to get an archive number for his PhD applications. We also want to try and include realistic CMB effects and extend to beyond CMB, say BA or supernovae. And then and some of the things that Nicholas has really been thinking about is how this relates to compression. Can you use to generate new compressed summary statistics that you could feed into other more traditional SBI methods? And it also explore the limits of DNN. I think D as 2,500 is approaching the limit of what a laptop can do. I made these plots during earlier today on that laptop. So, but if you want to go to say polarization, it starts to the n squared and n cubed things start to hit you. Yeah, lots of other things there. So there are my conclusions. And basically, if you want to chat to me about this, do. But it's more know that a lot of the reason why neural networks work so well is not because of their expressivity in practice, it's because they're plug and play. And what I'm trying to do here is to give you a plug and play linear version of that, just to check that it gives the same answer. So many thanks.
Fantastic. Thanks a lot, Will. Very interesting. For questions for Will? Yes, look at the front.
Of course, I love linear methods, so thank you for that. So I wanted to understand more this iteration, and there's two aspects of it. So one is that, of course, is the result at the end of the day still the proper posterior, in the sense of you're not updating the prior, so even though you're doing a resampling somehow.
And you do need to be careful. It comes from the fact that the likelihood here of D given theta doesn't actually care about theta being distributed from the prior or otherwise. You can condition on theta however you like and focus it. All these methods work, but that is also made much clearer when you look at it in the linear framework and compared to kind of wondering whether the neural networks do something funny under the hood.
Great. So, okay, that makes sense. And then the other question I had was, you made this comment that you somehow have to have a generative model for the data, but if someone just handed you a bunch of, like, why can't you resample? Why are you regenerating samples drawn from with different thetas? That as long as you have enough examples in the vicinity of where your linear thing is going to be, that would seem to work fine. So why do you keep having new colors show up as opposed to just masking out the ones and kind of, I don't know, important sampling the thetas, if you understand what I mean?
It's a good question. My instinct, although I haven't tested this, is that whilst this picture looks fine in low dimensions, I imagine in high dimensions, you wouldn't have many samples in the region of interest because you've got more, the high dimensions is big. And although it looks like it's got a nice spread in 1 + 1D, in 6 + 2,500 dimensions, there are probably no samples at all around here.
Hi, well, nice talk. So in the general kind of, well, in more realistic cases, you wouldn't be able to visualize that plot there to know that, say, the joint looks like linear in the region of your observed data. So have you thought of any, say, algorithmic tests that would know how many iterations you would have to do or when to stop, or how how inaccurate or accurate your approximation is where you start.
So yes, not long enough, but I have thought about this. So at the moment, the convergence basically is when the KL divergence levels off, the KL divergence between the prior and the posterior, i.e. when it's no longer contracted. But that's a pragmatic answer. Ideally, you'd have some kind of model comparison way of doing it. And what I didn't show you, because I wanted to spare you the maths, there was also an expression for the evidence that in principle you could use to select how many iterations you've done to go and think about the data.
Thanks.
Yeah, thanks for the nice talk. I was just curious, how would you say this compares? So there have been like also, as you know, in Munich, some kind of works on kind of variational inference with like super high dimensional Gaussians. And so like in a way, like it looks a little bit like kind of variational inference with like a partial amortization depending on like some kind of evolving prior or something like this.
It's a good question. I think in reality, the variation of inference probably will be quite linear under the hood. So
Right.
there probably are a lot of common things between it.
Okay.
And I need to check how much I've reinvented that versus this here. But it's more that these are things that you can handle on a laptop and understand these, which makes
Right.
it quite powerful.
Further questions for Will? Got a few more minutes.
I have a question, which I would sort of cast out to the room. So it's kind of hidden at this point here at the end, where basically I mentioned that in order to focus the parameters around the data you've observed, one natural way of doing that is using the posterior of the last round. So my question is, if the posterior is the answer, what is the question? I suspect the answer is the posterior or possibly a slightly broadened version of it, but I don't know how to actually say I would like to target my simulations around such that they generate the data I've seen. I'm not sure why the posterior is the right answer there. Anyway, Lucas?
Yeah. There's actually, could you go back to the joint distribution part? This actually might be a question for Casey and indirectly a question for Will. But so Casey, you said something about in this 1+1 dimensions, the data being linear in the slice there. Could you come up with, okay, so you don't want to use neural networks for the actual SBI, density estimation step. Could you come up with a scheme like a neural network compressor from the massive data space that conditions your compressed summary statistic to be favorably shaped or linear, such that this would become, that this downstream task would become easier to work with, it may be easier to visualize?
The answer is yes, and that's actually what Nicholas spent most of his time doing, was trying to get to do some compression stuff, because that's what stops us going high. But it's a much longer talk and much more inchoate, I think.
Do you have any, I mean, give us a hint as to any, did you come up with any specific ways to condition the compression outputs to be?
It ends up looking a lot like Moped in the first instance, but
Oh, cool. Cool.
Last chance. Going once, going twice. Let's thank Will again. Okay, brilliant. And so again, it's 25 minutes, but it's 18 talk. So I'll give you a 5-minute warning. Yeah, exactly. Anyway, up next is someone from UCL that I don't think I've ever met.
Yeah.
Right? It's good to come here to meet you, and take it away, please.
Thank you. Hi, everyone. Good afternoon. I'm Purvasha. And today I'll be talking about decorrelation, and I will be talking about it so this particular research is in particle physics, but I think it has applications outside of particle physics as well. So if anybody is interested in the work, let me know later on. And here's my list of collaborators. 2 of them are in this room, Olaf and Mikhail. So if you have any questions, feel free to ask them as well. Okay. Okay, so let's get started. So as I said, the data that we are dealing with comes from particle physics. So we are looking at these collision events that's giving rise to these jets of particles. And if you're thinking about what our data looks like, our data is basically like the kinematic and the topological features of these jets in some sense, right? And what we are looking for is we are looking for interesting events, right? That's basically what we're looking for. So if you think of the experimental data that we get from these experiments, you can think of it coming from one of two processes. So background will refer to anything basically known physics, and signal is the events that we are interested in. And so for this talk, they are events that could be explained by standard model, but just think of them as the event that you're really interested in, right? And so you can think of this data as coming from this mixture of the background and the signal, where lambda will give you the proportion of the signal in the data. And what we want to do is we want to test for whether lambda equals 0 or lambda is greater than 0. So is there any signal in your data or is there no signal? So this is just a toy example. Data is obviously not two-dimensional, but to just give you an idea, usually this signal appears as a collective anomaly. So the red points you see there are the signal. So they're sort of clustered together in some sense, and they appear in the same domain as the background, right? So that's sort of the thing that we're looking for. So let me quickly talk about our data sources. So we have been talking a lot about the simulations. So obviously one source of data could be the simulations from the models. So we have background simulations from the background model, signal simulations from the signal model. And then we have the data, which is unlabeled, right? So it's from this mixture of background and signal, but we don't know which of them is background and which of them is signal. So traditionally, you could say to do this test of lambda equals 0 versus lambda greater than 0, why don't you just train a classifier against background and signal and use this classifier to see if there's any signal in your data, right? So you could simply do that. You could do a likelihood ratio test. You could estimate PB and PS using the simulations. There's so many things you could do. The problem, obviously, is, as we have been talking about in this workshop so far, is that what if you don't trust your simulations, right? So these methods would then be trained on these simulations. And so if your simulations are misspecified, then you might actually miss your actual signal. And if your simulations are misspecified, you could also have a problem of what you're finding. Instead of it being signal, it could just be differences between your true background and the misspecified background, right? So how do you deal with this misspecification? Which is why what we're going to do today is we will focus today's talk on bump hunting. And so for non-particle physicists here, bump hunting is literally that. We are searching for a bump. And so the idea is that the background follows this smoothly falling distribution, and the signal appears as a bump. And usually there's this feature called the resonant feature, along which this happens. So you see this signal bump on top of a smoothly falling background. And testing for whether there is signal or not is equivalent to looking for a bump, right? And this bump hunting is done only on the experimental data, so you don't use the simulations here, right? So you're only performing the bump hunt on the experimental data, no simulations in the picture. So I'm not going to completely describe what the test we use is, but if you're interested, our paper just came out today, so feel free to look at the test in the paper. But the idea is that you have the signal region, you expect to see a bump in the signal region. You throw out the signal region, fit a background model, like a smoothly falling background model on the side bands, and then you extrapolate it in the signal region. And then if you see in your real data, is there extra data, right, on top of what you fit? So that's generally the idea behind the bump hunt that we do. But now the problem is, like, this would solve the problem, right? You're only using experimental data, do bump hunt, all good, all done. But the problem is the lambda is usually extremely small, so you can't always find the bump, right? So what do? We had this extra simulated data, right? We had the simulated data and we had this classifier that was able to separate the background from the signal simulations. And the feature that we had in the earlier page was just the resonant feature, right? But we have these other features that I said, the kinematic features, the topological features. So you have these extra auxiliary features. So we say that, what if we use this to do a signal enrichment step, right? And this is pretty common in particle physics. So nothing that I'm saying now is new to particle physicists as such. So, but the idea is that instead of doing the bump hunt in this whole space where the signal is quite small, what if you could put a threshold or a cut on the classifier? So imagine you create this decision boundary, and what if you do the bump hunt in this restricted area? So in this restricted area, you can see that the signal proportion is much higher, right? So you would see a much taller bump. So you're sort of enhancing the bump, and then you do the bump hunt test in this restricted space. Okay, so let me again go through the process. So we have the simulated data that's used to train this classifier. And then using the classifier, we cut on the classifier to signal enhance, and then we perform the bump hunt on the enhanced data. Okay, so this is just a table that shows that. So now what's the problem with this thresholding? The problem is that now we are looking at the bump hunt problem in a constrained space, right? And so what happens is, this was the distribution of the resonant feature, the mass. But now you can see here that after you apply this threshold of classifier greater than 0.5, the background shape has changed. So the background itself now has a bump, right? So you're looking for a bump on top of a bump, which is a much harder problem. So we don't ideally want this bump. So this is where decorrelation comes into the picture. So what we want is, ideally, after you apply this cut, you want this gray distribution to look the same as the left side distribution, right? So that you can see the bump on top of it. So what can we do? So to avoid the sculpting, if we have that the classifier that you're putting this cut on is independent of this mass variable, the m variable, then this distribution will look exactly the same, right? So if we could guarantee that the classifier is independent of this mass variable, then we are all good, right? So let me come on a discussion of existing decorrelation methods. So these are called decorrelation methods because they don't always go for independence. At least the first few methods that were in this domain were not going for independence. So we are going to continue calling it decorrelation, but a lot of the methods actually make them independent. Okay, so I just want to clarify that. So there are three ways in which you can do this. One is you can make the inputs itself decorrelated of the protected variable, of this resonant variable, right? So if you make the inputs independent or decorrelated, then your classifier is also decorrelated, right? The second thing you could do is, when you're training the classifier, you train the classifier to be decorrelated, right? And the third approach, and the one we take, is you give me a classifier and we post-process it to make it independent of the variable, right? So these are the three ones. And the second one, the way they do it during the training is usually using a regularization term. So you would put like a penalty function where you penalize it if it is not decorrelated, and that's how they do the training process. The way our paper and the CNOT's paper does it is we consider optimal transport problem, which I'll discuss right after this. But there are some other methods as well that can do it. I think the beauty of the post-processing method is that you can let the domain experts create a really, really powerful classifier. And then as a secondary step, you can now make this classifier independent of the protected variable. So it's much more cost effective in some sense because you already have this trained classifier. You don't have to retrain it again, right? Okay, so as I said, what we want to do is we want to find a transformation such that we can make cuts on this transformed classifier, and this transformation will now be independent of this protected variable, the resonant variable, for the background data, right? And the way we do this is we don't want to lose classification power, right? Because if your classifier can't classify anymore, then there's no point, right? So we want the transformation to be as close to the original classifier as possible, while making the transformation independent of the protected variable. And this is all for the background. And we keep the marginal the same. So I'll come back to this point. Just hold on to this for a moment. But we are going to keep the marginal the same. And the solution to this optimization problem is actually an optimal transport map that takes the conditional of the classifier given the mask to the marginal of the classifier, okay? And if your classifier is univariate, then this problem actually has a closed form solution, which can be written in just terms of the CDF of the classifier and the conditional of the classifier given the protected variable. So it's basically a very simple term, and all you have to do after this is estimate the conditional distribution and the marginal, and you're done, right? Okay, now coming back to the marginals being the same. So you technically don't need this condition at all. You can choose the marginal of the transformation to be whatever you want. Any favorite distribution you have, you can pick it. The change will be that then you will map the conditional to whatever marginal you have chosen. And similarly, the CDF here will be whatever marginal you have chosen. And the good thing about this is because this is a CDF, so it's a monotonic function, right? So it doesn't really matter whose CDF you take because they have to be monotonic. So like the transformation doesn't really change when it comes to making cuts, just your cut would change, right? So it doesn't matter that much is the point. So we just chose to keep the marginals the same. So just a picture, graphical representation of this. So we take the conditional distribution, we force it to become the same shape as the marginal distribution. And coming to the sculpting problem, so this was the problem before. The background had a bump. And now if we cut it on the transformed classifier, you see that there's no longer a bump in the background. So even after the cut, it looks the same as it did before the cut. So as before, after the trained classifier, now we put a transformation on it, and then we cut on the transformed scores instead now, right? Okay, so now there's this cool idea of what if you want an intermediate step? So think about the case where I said where we train the classifier to be decorrelated in the same step as when we are training the classifier itself. So I said that you would add a regularization term, right? Now the regularization parameter lambda will control how decorrelated it is. And so in this case, what we do is we say, what if we stop in an intermediate step? So we are transforming this red curve to the blue curve, but what if we stop on somewhere in between in the path of this transformation? And turns out that one of these gray paths would just be the linear transformation of the original classifier and the transformed classifier. And this would give you like an intermediate step. So not a fully decorrelated one, but maybe with slightly more accuracy, right? Okay, now let me quickly come to the experiments because we have only 5 minutes left. So I won't go into the details of exactly the description of it, except that this is like a benchmark data set to compare these decorrelation algorithms. And these are the plots of before applying the decorrelation. And you can see that the background pretty much overlaps with the signal, right? You can't tell the gray and the blue ones apart. So this is the problem if you don't do the decorrelation and just do the signal enrichment step. And the top row, if you see, is after the decorrelation. And you see that you can actually see the bump in all of these cases. So as we move right, the classifier is increasing. And now you might say that, okay, you have decorrelation, but can you actually, like, do you have any accuracy? Like, do you actually do a signal enrichment? And the answer is yes. As you can see on the bottom row, the amount of signal increases as the classifier increases, right? So you do see that the blue peak does become bigger and bigger. So the bump is getting bigger, right? And this is a quick comparison with some of the other methods. So to quickly tell you, the x-axis is increasing accuracy, and the y-axis is increasing decorrelation. So ideally, you want to be somewhere over here with extremely high accuracy and extremely high decorrelation. But obviously, that is not possible because it's a trade-off. But I would like you to look here, which is at a pretty high decorrelation level, we have quite a high accuracy. And so it's performing competingly well with other methods in the field. And finally, we did something that we haven't really seen before, which is putting this together with the bump hunt. So, okay, we have done this decorrelation, we have done the signal enrichment. Did it finally help us gain power when it comes to the actual signal detection test, right? And so the left plot is without decorrelation, the right plot is with decorrelation. The x-axis, the 0 point, is when if we don't do any signal enrichment. So if you did none of this and just went ahead and did the bump hunt, right? And so just comparing the left side plot and right side plot, you see that this is unpredictable, right? The left side plot is unpredictable because here you get the bump. So it's very unpredictable when you will be able to detect the bump on top of the bump, right? So it's a very misspecified problem. And so it becomes very hard to detect the bump and predict what it's going to do. Whereas on the right-hand side, you see this nice behavior of increasing power. And you do see that with higher classification power, like with higher values of classification cutoffs, you do get increasing power. So the signal enrichment is helping, the decorrelation is helping. And a quick example of some robustness results. So the takeaway from this one is that we have a background, 3B background that we are training the models on, but we test them on a 4B background. So this is a case where the background is misspecified. So your simulations are misspecified. Are we still able to do this correctly? And so the bottom row here is the training background, so the 3B background, and you see that the shape is maintained. The top row is the 4B background, which is the one we are testing for. So the top row is the case where we have trained on a misspecified background. And we see that the 4B background still retains the shape as the classifier increases. And now just to show you some power curves. So this is for the 3B, which is the true training background. And you see that again, similar to the previous example, the power is increasing with the signal enrichment. And you see that on the left-hand side, again, without decorrelation, it is really unpredictable. So you really have no idea what is going to happen to your power. So you should be doing the decorrelation if you're using the signal enrichment. And this is for the robustness case, which is, it's been trained on the misspecified background, and we're trying it on the 4B background now. And you see that, again, the left side without decorrelation is really unpredictable. On the right side, you see that there is one dip, but that is to be expected because it is misspecified background, right? But we do see that we sort of have sensible results where we do see that there is some increasing power, and at least we are keeping at the same level. So it is working for the misspecified background. Like it is still retaining the shape, and it is still working the way we would expect it to work. And so finally, just comments and discussion. So what we are doing is you give me a pre-trained classifier and you give me a variable you want it to be independent of, and I can make that happen. So we can make any classifier independent of any protected variable that you want it to be independent of. We can handle multiple and multivariate protected variables. So we don't address that in this paper, but it should be very easy to implement. Extending to multiple or multivariate classifiers is more complicated because, as I said, it's a closed form solution if the classifier is univariate. If it is multivariate, then it won't be a closed form solution, but you can still find the optimal transport map. It will just be more computationally expensive, right? And finally, we are giving a range of transform classifiers in some sense using this idea of geodesic morphing. And we also showed that it's robust to some kinds of model misspecification. In the future, it would be interesting to think of what kind of model misspecifications we are robust towards. So when would it really start failing? For what kind of misspecifications? And finally, we also showed that the signal enrichment step as well as the decorrelation step, both of them are indeed increasing the power of the bump hunt. So they are both useful steps to be doing. So finally, as I said, our paper just came out today. So if you want more details, that's where you will find it, or you can email me. So either way, thanks.
Thank you.
That's very interesting. I'm sure my colleagues on Atlas would be curious to read your paper. Are there any questions?
Hi,
Hi.
very nice, Pravasha. Is there a plan then to use it on some particular analysis in the near future?
Yeah, I would hope so. So we haven't been working on it yet, but I'm working on it. Like working on getting a experiment to hopefully use it on.
Good.
Thanks.
Yeah, very nice. Tobias Golling, University of Geneva. This geodesic that you can use to go between the correlated and decorrelated, do you see any utility application of that? Is there any use you have in mind?
Not really. So I think if you see in our plots, at least in our case, where is the plot? So you see here, there's like a jump here. So I don't know, like if you're somewhere here, like I still feel like if you really want your statistical test to be valid, you would want to go for as much independence as you can. But if you really think you're losing a lot of accuracy, then it might be worth trying one of the intermediate steps. But then there's the question of, then do you trust your result? So yeah, I would say you should go the full length if you can.
Thanks.
Igor, it's got a question online.
Yes, I'm a little bit unsure of what is meant by independence here, because you know, typically if you want to establish statistical independence, you look at objects like copula and see that they are uniform or something like that. So what is meant by independence?
So if you look at the copulas here, they should be independent. So we are basically statistically making it independent. So you see this plot of, so basically for every M, we are forcing the conditional density to be equal to the marginal density. So by definition, it becomes independent. Does that make sense?
No,
Okay.
because M in your case as a parameter is not
No,
available.
M is the resonant variable. It's not a parameter. It's
So
you're trying to make
it's according to you, it is a random variable, right?
Correct. So M
Okay,
is a
so
random variable, H is a random variable.
Okay, so is it possible to show a copula of H versus M? Then one could maybe believe you.
Yeah, okay. Fair enough. But yeah, but I guess the idea is that we are making, like, we're forcing these two to be equal. So by statistical definition, we are making them independent. But I agree with you that it would be nice to look at the copulas to see how close to independence it's getting. So yeah, that's a good idea.
Other questions? May I have one quick one? So say you can take any classifier and make it in, you know, uncorrelated to basically any combination of variables.
Yeah.
Are there no, I mean, there must be some breakdown to that.
Yeah, I'm sure, because so for example, if you take all the features that you have trained the classifier on and make it independent of all of those features, then your classifier has no more information left. But I guess the idea is sometimes there could be, so in this case, for example, your resonant feature M may not be, it's not an input to your classifier, right? But some of the variables that are inputs could be related to this. So I guess in some sense, what you're doing is you're removing the marginal effect of this M variable. And you could think of this in many examples. Like somebody was saying, let's say, you know, you're training an algorithm for whether somebody should get a loan or not. And let's say, like, you don't want this result to depend on somebody's height, right? So I mean, one could argue that maybe it should depend on height, but basically you shouldn't lose information if you remove height. But if there is, then maybe there shouldn't be. So I guess that's where we are at this. So it does have, I think it does have applications to fairness as well in that sense. That if you want an algorithm to be fair and not depend on some protected variables, you could take this algorithm, make your classifier independent of these protected variables.
We've got one final question.
Very quick, very nice talk. Thank you very much. What are the constraints on the features, either the ones you did correlate against or any of the others involved? So for example, can they be discrete or binary?
Oh, that's a good question. So yeah, that should be possible, because as long as you're able to get the conditional CDF, it should work.
Okay, thank you.
Yeah. But that's a good question. So we haven't done it, but I think it should be doable, because you would just have two of these, right? Like, let's say it's binary. If M is binary, you just have H given M1 and H given M2, and you just make them both equal. So that would actually be an easier problem than the continuous case.
Very good. Let's thank Shige.
Thank you.
Into our last talk of before the coffee break. And this is a slightly longer one. So you've got 45 minutes, which means I'll give you a 5-minute warning after 25. But take it away, yeah.
Yes, I'm very happy to be here, actually. I did my Erasmus 8 years ago here in Peru, so I'm quite happy to be back. It feels like coming back home, so I'm very happy. Yeah, it's nice to speak to all of you. A lot of people maybe having way more knowledge about statistics than I am. Still, I got the nice opportunity to talk about statistics of generative models in this statistics meets ML meeting. So the first thing I did was like, I went onto ChatGPT and asked it to, can you draw me a picture of how you would imagine London meets LHC? And this is kind of what you see in the first slide. What you get out is like this nice picture for London Eye being merged in this apparently LHC tunnel, but there's also a tube going through. It might be dangerous, so we maybe shouldn't do that. Yeah. All right, so what I thought about doing is first of kind of repeat, there will be some repetition for sure, because a lot of people have been talking about generative models already, have been talked about certain aspects, so there will be certainly some overlap. I still try to put maybe things in a little perspective on how I think about these, so there will also be, I have to do some disclaimer. I'm a particle physicist, so I will have a particular point of view on certain stuff. But the idea I have is like starting with a short introduction, very roughly, what the deep generative model is, on how I think about them. And then go into some strengths and weaknesses between the different types we usually use. And then also dig a bit into uncertainty estimation, something Tilman already mentioned with Bayesian neural networks and things we already heard before. I will also kind of repeat again the classifier test and reweighting, which has been mentioned again by Tilman and also by Gregor. And then the very last bit, which is something Louis kind of reminded me essentially in every break, to really talk about this data amplification topic, which I think has already kind of been answered by Gregor already yesterday, but I will kind of rephrase this stuff. And then after that, there will be options to have just an open discussion, either only on this data amplification topic, where there's also other experts in the room, as I just said, like Gregor or Tilman, and any other question which we might have. And this can be either questions or just an open discussion about opportunities we can do in the future. Okay, let me start with the introduction part. And I always like to start with this figure, which I kind of adopted from the paper from Tilman and Jonas, because it nicely represents how we think about LHC analysis in a kind of oversimplified way, where we have this very complicated simulation chain, which is very, very crucial in order to have something which we compare. Because at the end of the day, we have a fundamental theory like QFT, which we need to compare with our measurements. And those two objects are fundamentally different things, because one thing is a mathematical formula, the other things are signals and detectors. So we need to translate that. And our tool of choice for doing this translation are Monte Carlo simulations. And of course, if all works out, we potentially do pattern recognition. We potentially find new physics. So if the answer is, do we find new physics? And the answer is yes, we're all happy, because some of us probably gets the Nobel Prize, we go to Stockholm, we celebrate. If the answer is no, we're slightly unhappy for a while, but then we just go back. We maybe go back to the blackboard, modify our theory, we might also just have to optimize our simulation chain, or, and this is also what the upper red curve should tell you here, this one, we also might just need to build different experiments. Maybe we're just not sensitive enough to what we actually want to looking for. Now, the next thing is, of course, how does this analysis chain at the LHC, is this connected with deep generative models? And of course, this is just very much a subset of things which are possible. But this kind of includes stuff which has been presented here. Like, for instance, unfolding. We heard a lot about that from Vinny and also from Tilman. And we heard also talks today and yesterday about simulation-based inference. I'm also excusing everyone I forgot on that list, so I'm sorry for that. And there was also some mentioning about color simulations from Gregor yesterday. And then there's this other point, which has already kind of been advertised by Tilman, which is something I also want to present and talk about, is the so-called madness approach, which goes in this very early stage at the very beginning of event generation, where we still kind of understand everything. And then I also want to mention a different perspective on the SPI method, which is the so-called matrix element method, because I think it's very nice. And there's also a poster about it. Okay. There's also, when we think about deep generative models, of course, we also often look into what's out there in the industry. And something which is kind of remarkable was in 2018 or 2019, when there was this GAN picture drawn, which they called Edmund Bellamy or something. Tilman always knows how this guy is called. And if you look very, very closely down here, there's like also the loss function of the generative model. And for whatever reason, this actually has been sold for almost $500,000 US. Nowadays, most of the time when people are using generative models for generating images, most of the time it's based on diffusion models. And there has been, like, I think last year, these fake images of Donald Trump running away from the police, I think. And most of the time when we use generative models in the context of text generation, like ChatGPT, for instance, it's almost certainly involves some kind of a transformer model. So these are kind of the things we have around every day, and probably most of you have been used these stuff already. Now the question is to go a little bit more from more math side, what is actually generative model? And most of the time what we consider is we have some truth probability or data probability, and I'm probably using those two terms interchangeably today. And what we are most of the time really interested in is model this probability density with this network parameter omega, and then actually sample from that, new samples which follow your data probability. And then depending a little bit, how do we actually have access to the truth? This kind of allows us different ways of training our networks. Usually we can have these truth probability either explicitly. So for instance, in particle physics, maybe it's a differential cross-section, or just any other problem where we can just explicitly write down what P data is, or we just have it implicitly given. So we have a data set which with an underlying probability distribution following P truth, but we don't have it, but we only have this set of data points. And of course, in particle physics, this is, in broadly speaking, event generation, colorimeter simulation, unfolding, what we've just heard a lot about it, and also in matrix element method, the transfer function, which is essentially the forward simulation, which Lucas was asking about. And of course, there's multiple of these types of different generative models. We have GANs, we have flows, we have VAEs, diffusion, etc. So the question is, can we bring a little bit more structure into that? So it's not necessarily only strength and weaknesses, the next point, but also trying to put some structure in the landscape of all these deep generative models. And I also remember yesterday when some people already looked into my slides, we had a little bit of discussion. Is it really true to put certain things in certain parts? Because I would certainly agree, while we all agree that the Wasserstein GAN is part of a GAN, the boundaries are kind of floating between diffusion models and normalizing flows these days, right? So you should not really think about these things as a pure strict classification, but like just one way of seeing it then. And as I just said, on one way I have these generative adversarial networks, which came out actually in 2013 and have been used very a lot in the beginning for various kind of approaches. Like I think the first GAN in HAP was the Carlo GAN for Ben Nachman and friends. And even we in Heidelberg back then, when I was a PhD student, used them quite heavily. And we figured out quite early that it's very difficult to train them because they have this, in one way, very nice feature of just having this competition between two networks. it's also very nasty to train them because you have these two networks competing with each other. And it's like having two very, chess players that don't really like each other. So it's sometimes very difficult. And I had very hard nights sometimes to get this stuff work. So nowadays, most of the time, we not necessarily use them anymore. And another thing, which is also very important, which I already just mentioned, is that while these things can be categorized in these different ways, there's always some interconnection. So if you, for instance, sit down and look into the math of a VAE, starting from doing this elbow loss stuff, etc., and then look about what is the diffusion probabilistic model doing, they're very much linked to each other. So a hierarchical VAE is very much linked to a diffusion model, where you just replace some of the assumptions with other assumptions, which allows you to reparameterize the loss and then just train the entire system differently. And on a similar note, continuous normalizing flows and this conditional flow matching, which we also heard about it before, they're very much similar. The question only is, how do you parameterize the loss? In one way, you really try to parameterize the likelihood and use that as an object. In the other case, use a trick, link this likelihood to some continuous flow, which you then just regress in a normal way. And then there was also another nice paper from Max Welling and friends from the ML community, which have been showing that actually VAEs and normalizing flows, they're not that different actually. While of course normalizing flows, we know they're invertible by construction. For VAEs, that's not the case. But there's actually, they're living on a spectrum. So you can also build something which is kind of invertible, but not really. And this is the so-called subjective virtual VAEs. As I already mentioned, it's not just that we can use these kind of things interchangeably, so it kind of depends on which application you're doing. Of course, sometimes you combine these things. So you're not just relying fully only on normalizing flow, you might be using a normalizing flow combination with a diffusion model or normalizing flow in combination with a GAN whatsoever. So any kind of hybrid you can think of, you can do, like you can have this butterfly elephant here, for instance. And I'm kind of wanted to highlight a little bit those two models here, which are the bigger class of diffusion models and maximum likelihood models, which contains these normalizing flows and all these autoaggressive transformer stuff, because they're really nowadays the most used one, which gives us the highest precision and the highest fidelity in most of the cases. But then, of course, you can ask yourself, okay, but which one shall I use? Shall I use a diffusion model? Shall I use a normalizing flow? And the clear answer is there is no clear answer, because in the end of the day, there really is not a Swiss Army knife architecture, or something I prefer to say, but only makes sense in German, is the so-called eierlegende Wollmilchsau, which just means that there's no single architecture which can serve all purposes at the same quality. So it really depends on your application. And this is, again, just a rough comparison. Like most of the time, if you think about diffusion models, we have in mind they're state of the art in precision. So all of the very good results for the Carlo challenge were diffusion models. They're very fast and stable in training. But if you're really interested in getting an approximation or a calculation of the likelihood, you can do that, but it's not super fast. At the same time, if we have something like a normalizing flow, they're also very stable. We can run them equally fast in both directions because they're invertible, which is handy. And because of that feature, they also have a tractable and fast likelihood, which comes in handy depending on your application. Of course, on the other side, because of this construction, it has to be invertible. There's some certain reduced flexibility and expressivity. And as I just said, it really depends on your application, which is your model of choice. Now, the very first thing I wanted to give as an example for that is a so-called madness approach, which in our case essentially only relies on normalizing flows. And it essentially does the following. So whenever you do Monte Carlo integration, the very first step, whenever you want to calculate integrals, differential integrals, want to throw event weights, you always do this with Monte Carlo, meaning you want to throw these points as efficient as possible. So the most stupid thing to do, if you're interested in this function f, so this black one, is to just throw these points in a flat way, because obviously you're highly oversampling the tails and undersampling the bulk, which is of course very inefficient. What you instead want to do, obviously, is important sampling, which means you want to throw more points in the bulk and less points in the tails. somebody gets a call, whatever. And of course, you can very often, the question is, how do you find this function which perfectly maps out your integrand while being able to actually sample from it? So it's not just sufficient to have a function which kind of copies your integrand. You also need to be able to sample. And that's a non-trivial question. And one of the things you can first do is like, well, maybe I can first simplify my problem by saying, well, maybe I can split up my phase space into different regions. So I find an integrand or sampling function which describes the one peak on the left, and I find a different sampling function which describes my peak on the right. So just split it up, and then later on, I just sum up both contributions. And this is so far the basic procedure essentially in all phase space generators you have. Like if you use Sherpa, Markgraph, they all use that. Okay, this is the starting point. Now the question is, how can we improve that? Because most of the time, this standard way of doing this important sampling is based either on physics mappings we know of, or we use some, Tilma would call it prehistoric machine learning methods like Vegas, but the Vegas works very, very well. The only downside with Vegas often is it cannot really catch correlations. So what we said is like, well, instead of just using Vegas or just using this physics stuff, maybe we can just use normalizing flows, because normalizing flows have these neat features that, first of all, they can give us a probability, which is what we need. This is this G here. And we can also sample from it. This is what that means here, with sampling from that function. So we can then sample, use this normalizing flow for the parameterization. And on top of that, something we also implemented in Madness is when we do this multi-channel splitting, what you in principle do is just a partition of 1. So you need to make sure that this weights for each of these channels sum up to 1. And this is kind of the only condition you have. But most of the time, people have very good assumptions of like physics-based, how you build up these weights based on your multi-channel build-up, which is built upon Feynman diagrams, essentially. And we said like, well, maybe we start from this very good assumption, but we just fine-tune them a little bit, twiggling around by using an additional neural network. And if we put everything together, this is what you see on the right, we get a normal Markgraph approach, which on the left-hand side, you see a relative standard deviation. On the right, you see an unweighting efficiency, which effectively tells you how efficiently are we sampling. And if we include all of the features in Madness, which we have, like this multi-channel approach, doing efficient combination of Vegas with all of that stuff, we're getting essentially from an unweighting efficiency down here to up here, which tells you in this particular process, improvement factor of 15. What does this mean? Improvement factor of 15 in unweighting efficiency really means a speed up effect of 15. Meaning if I want to generate 1 million events of that particular process, and it usually takes, let's assume 15 days, it would not only take 1 day. So it's a huge speed up we gain just by using this more advanced method. Something I'm not going to go into more detail now, but something I still want to mention is our very latest paper from just like 2 weeks ago, where we also now have a fully differentiable version of all of that, because we find in a lot of discussion, it's very helpful if you have gradients about everything. Now we can ask ourselves, okay, that's nice for Madness. And in Madness, we also don't care that much about the actual uncertainties of the neural network, because Madness is just used as a proposal function. At the end of the day, you still just evaluate your full integrand, your QFT observable, and the uncertainty is fully driven by your Monte Carlo uncertainty. But this is not true if you use these deep generative models in other cases. So if you do it for unfolding, colorimeter simulation, where your actual sampling is already what you actually want to look at, you better have some kind of idea of how you estimate these uncertainties. And this is where these so-called Bayesian neural networks come into play. But first of all, what do we usually have and what do we want? So what we most of the time have is we have some fixed input and we get out some fixed output. But in particle physics, we're not just interested in results, we're interested in error bars, which means what we want to have is we want to have a fixed input, or if we have a fixed input, then we want to have a probabilistic output. So maybe we want to have a mean with an uncertainty band. Question is, how do we achieve this? We heard kind of these things already. We can do normal ensembling, repulsive ensembling, Tillman mentioned, or for instance, so-called Bayesian neural networks. What is the idea behind Bayesian neural networks? For those who already know that, I will try to not be too detailed into these things, but I still wanted to repeat it, that the basic idea is very simple. It just means instead of just using a weight, which is just one value and determined after training by one value, you actually define your weight as a distribution. In principle, this distribution is completely arbitrary, but in order to actually make sense of that, in sense of we want to actually calculate something, we most of the time assume it's Gaussian and then do kind of a, you know, central limit that if we have a lot of weights and they're all Gaussian, in the end of the day, I can still model something which is not Gaussian anymore. And what you then in the end up get is you have this Bayesian neural network, which, by the way, naming this entire thing a Bayesian neural network is kind of a naming disaster, because the only really reasons why they're called Bayesian neural network is that at some point where you try to approximate this posterior function, which you're interested in, with some neural network, you use Bayes' theorem to kind of reparameterize the problem. And this is the idea behind it. So the idea is you want to get this predictive distribution given as you're averaging over your weights from your distribution. And of course, in principle, this posterior of your weights is intractable. So how do you do? You can either try to use Bayes' theorem and integrate everything out, which is complicated. So what most of the time is be done, which is very similar to VAEs, is you approximate it with a neural network. This is so-called approximate posterior. And here in principle, there goes another approximation in, which is that you really assume that the thing you parameterize really is just some Gaussian. So in the end of the day, instead of having one network weight, you're training two, which means you're training a mean and a width. Okay. And this comes with kind of two nice features, because if you do all the math, you end up essentially with this B and N loss function, which gives you the standard log likelihood part, which you kind of have all the time whenever you derive a loss function for your machine learning problem. But now this is averaged over the weights you're sampling from. So this gives you a mean. And then on top of that, you have this KL divergence, which is actually very cool, because here this KL divergence gives you naturally a regularization term of your weights just from the definition starting from the Bayes theorem, which normally, if you have a normal loss function, you put in by hand in some ad hoc way. We say like, okay, maybe I want to regularize my weights. So I put in an L2 loss norm, for instance. But here this just comes in naturally, which is quite helpful and stabilizes training, which most of the time means you're not overfitting. Now you can ask, okay, I have this. How can I use this in an application? And of course, I don't want to talk about applications either they have already presented or have not worked on. So I want to talk about the so-called matrix element method. And what is so nice about it? The matrix element method is very similar to what we have heard in a way that it tries to give you a handle on the actual observable likelihood of a given recall level event given some theory parameter theta. Okay. The problem is, as has been already pointed out, that most of the time we only have handle and theory knowledge over this hard scattering momenta, because this is something we can calculate. So we can calculate what is Px hard given a theory parameter, at least at leading order. At NLO, how to define this properly is a different topic. And then, of course, if you then want to transfer that knowledge onto recall level, in principle, you have to calculate this entire integral, where you integrate out your X hard momenta, and you have to convolve this with this transfer function. And this transfer function redescribes the convolution from starting a hard momenta going to the recall level, which is literally exactly what Tillman said, the inverse of the unfolding. So unfolding would be the inverse process. Something which is also in that, which is of course something we missed in the beginning, but it's very important, is the so-called acceptance function, which just takes into account that at recall level you apply cuts. And this is something you have to take into account when you do this calculation. So, and how do you do this? So what you now can do is, okay, we have madness. So we can use madness to improve the importance sampling bit, because of course, in the end of the day, when we want to estimate this integral, we do this with Monte Carlo. So we use our madness approach using normalizing flows to improve the importance sampling for getting a better estimate of this integral. Then this hard differential cross-section we can calculate, in this case for theory knowledge. And on the other side, we can also use a normalizing flow to describe the transfer function. Because again, the normalizing flow can do both. It can be used for sampling, but it can also be used in order to parameterize densities, conditional densities. And one thing we had to do here, and it's kind of like this hybrid version of this butterfly elephant, we figured out why the normalizing flow is very handy because it's fast in parameterizing these functions. normalizing flows sometimes have trouble to catch all the correlations very quickly. But then on the other side, we have these we have these transformer models, which come in with this attention mechanism, which is very helpful to catch correlations. If you want to combine, okay, how is a chat level observable defined to parton level observables? So we combine the idea of having a transformer and a normalizing flow in the transfer function. And some of us came up with the idea of calling it a transformer. And I remember one of the reviewers of a paper said, it must be some misspelling because it must be called transformer, but you just didn't get it was our invention of the word. So what happens if you just put everything together? So here, this was a very simple EFT analysis where we have sampled some anomalous coupling. So in normal standard model, alpha would be 0. And here we were sampling some hypothetical world and where alpha should be 45 degrees. And then something is, now you see this log likelihood function, which you have seen in Aishik's talk before. So the more it goes up, the better it is on a statistical perspective. And of course, something we can calculate here because we have full simulation and full access is how does the truth look like? This is the blue curve. Then we can do the calculation doing with the matrix element method, integrating out this entire thing of the truth, convoluted with the land transfer function times acceptance function. What you then get is this red curve, which is our result. Then the width, like this width in this direction of this curve tells you something about the statistical uncertainty, meaning in this particular case, we have evaluated 10,000 events. If we would use less, this would go down. If we would use more, it would go up. And on top of that, you also see that there's also some error bar on the actual method itself, which in this case have been estimated from a Bayesian neural network. So we made the entire thing of the transfer function and Bayesian neural network, which then allows us to give us this uncertainty on this. And of course, the minimum would be the hypothetical measured value. And as I just said, here also a poster. Unfortunately, I'm talking now after the poster has already been shown. But I think, yeah, you can also go on the paper if you want. And the last, no, not the very last thing, but something I want to mention, but I can be a bit more quick because it has been mentioned before, is the so-called classifier test and reweighting. What I mean by this is, as we have already heard very often, you can use this classifier trick where you can train a weight. And instead of just using this for whatever thing, you can also maybe just implement that to actually reweight and improve your generative training, which has been first proposed in a so-called Dr. Gann approach. Something which people also try to work on, in particular Ben and I did, is like, okay, if I do this reweighting, this means I have weighted events, but very often we're interested in unweighted events. Is there anything we can do about it? And the answer is yes. Once you have this weights defined on your feature space, similar to omnifold, you can also pull them back onto your latent space, make them a function of the latent space, and then you can use a smart combination of normalizing flow and MCMC to now sample from your new reweighted events, you know, your effectively new latent distribution, and then pipe it again through your network, and then you get out your effectively reweighted distribution, but in an unweighted way. And this is kind of what you see in the right, where this laser approach, latent space refinement, just gives you a reweighted distribution, but the events themselves are unweighted. And of course, as Timon already said, if you're not interested in directly using it to improving your network, you can also use it as a classifier test, so kind of a way of testing how good does your model work. And I think I actually took that from a paper of Tillman where they tested this for instance, C+3 chat. And there you can, for instance, see that the generative stuff gets very low weights, which is an indicator in that particular case that was just missing a cut. Okay. Now I'm coming to my very last point, which is the so-called data amplification, which, as again, Louis keeps on asking, and Gregor already mentioned yesterday. But the question essentially is, and kind of the starting point of discussion, if I would like to say that, given you have n training samples, you have been trained your network on, how many more events ng, assuming ng is larger than n, can the model generate so that it can kind of effectively increase the statistics? I mean, I try to phrase it in some way that it makes sense, but you can still see like there's a lot of things which are still a bit vague. Like, what does effectively increase the statistics really mean? Because it really depends on what are you actually looking at. And there were some approaches and attempts to answer this question in certain scenarios, which comes under the name of GANplification, because the very first models back then, which were out there, were the GANs. So let's maybe just try to tackle this with GANs. And what they were trying to do is, for instance, what if we have a 5D Gaussian with some just 500 data points? I train my GAN on that, and then I sample way more points. And then because I know what my distribution is, I partition everything into bins of quantiles. Why do I use quantiles? Because if I have quantiles, I know what the probability density has to be in that particular quantile. And then, given the known quantile probability density, I can compare it to the number of points I've thrown into and get an idea how good this has been approximated. And then you can do this with this GAN, for instance, and you can see if I train it on 500 points, I can keep on generating points. And then at some point it converges, because this just means the network has a certain complexity and can only learn a certain information, which is there, but it can still oversample. In this particular case, this means if you would just compare 2000 sample points in your quantiles, it has the same value as the GAN, which has been trained on those 500 points. So there's some enrichment in this quantile approach. And then 2 years later, there was a different project. It was from, again, Gregor and Tillman, I think. I'm not sure who else was on that paper. And where it was like thinking, okay, this was a toy example, but what's happening if I do this for a colorimeter simulation, where I have way more complexity? The definition of quantiles still works, but it's a bit more involved. And then they have trained this GAN on 1,000 points, and then try to generate way more points. In this particular case, it was 1 million. And then they compare, depending on the number of quantiles I define, how much more value do I effectively get out of my GAN? And the first thing you notice, if I go for a very small number of quantiles, there's essentially no gain. So here's one case, essentially what has been trained on, and essentially overlap with each other, which is essentially tells you the informations, the very low moment informations like mean and things like that, they're already there because that's what the GAN has learned. But what the GAN can do, or your whatever density estimator can do, is like interpolate. So it might also be able to, based on this low momenta, sample higher momenta. And this is something you can only evaluate if you go to more quantiles, because then you have access to potential other fluctuations. And in this particular case, you can see, well, I'm oversampling here with 1 million points, but I effectively get the same quantile information as if I would have had 50,000 free data points. One thing you notice, while there is certainly some amplification in this particular point of view, you can also see that here I have 1 million points, which have the same value as 5K real points. So this means you can oversample, but a single point or single event which has been sampled effectively has a reduced statistical information. And they also did to check, is this a general thing for density estimators, or is this a particular machine learning tool? So they evaluated, okay, what happens if I do the same thing, for instance, with a histogram or for the KDE approach? And you can see that it actually also works. You can make this work, but of course, depending on the quality of your network, it just works better. So in this particular case, you can see that if you have this VAE GAN, this particular case, you already achieve the same quality being trained on 1K events than if you have a more simplified model being trained on more points. And this certainly also works if you now go to different models. So this also, we know this works from different models, because this is something been mentioned yesterday, as I said, from Gregor, where they did it with diffusion models, if I'm not mistaken. And there they also said, well, another approach to this, if we have BNNs, is let's estimate from our network the uncertainty it gives me out, and then compare this uncertainty of the network with the statistical uncertainty we would expect. And we can use this uncertainty information as another handle of understanding, is there some kind of amplification, which was, as said yesterday in the talk of Gregor, but also in this very recent paper. And this kind of brings me to the end of this very kind of rough outline of all these different things and different applications, and is the beginning of a potential open discussion of either the very last point or all the other points.
Thanks a lot, we have time for some questions or comments or opening gambits in discussion.
Okay, thanks for that, especially for the last section.
Of course.
So this question of gamification, sort of on the website, we have these sort of discussion points, and one of them is exactly about this, that if I imagine a very simplified version of the problem, and I've got points in X and Y, and I'm trying to find the gradient of a straight line through them, of course, I get a big uncertainty because I've only got 4 points. So if I imagine that these 4 points were very hard to obtain, I'm going to generate more points on the straight line. I generate 1,000 points, I get a very small statistical uncertainty, but I've got a big systematic still from the original 4 points, like you were saying. So I've gained nothing. So what is it about sort of particle physics situations that are different from that? So, I mean, Pierre Baldi this morning was sort of dismissing my simple example as just being shallow learning and said they're not comparable. But is there a longer answer than that?
So it's very much a personal view now, I'm going to tell you. So I don't think there's a fundamental difference. I think why it works is, I would generally say, in principle, if there's a certain amount of information in the data points, then there's a certain amount of information, and it's not like you can artificially increase the actual information content. But what is the trick why it works here is that, let's assume you have your information in your 4 data points or in this other data set, and meaning that all the information is in doesn't mean it's easy to extract it, right? And if I do this quantile method, it's a very simplified way of accessing some information content of my data points, which might not be the adequate way of extracting the possible content of the information content of my stuff. Now, if I have a machine learning method like a generative model, this is now able to have a better handle extracting not more information than is there, but more information than my very simplified method. So this is able to extract this information. But then, because I can do sampling, I can oversample, and then effectively what this means, I think about a little bit like the energy conservation. Energy is conserved, but the way in how the energy is there is different. So the information doesn't change, but you can translate this maybe before intractable information content into something which is now more tractable by your simplified method. If that makes any sense to you. That's at least how I feel how this works. So, and go a bit further, is something which also Gregor said yesterday. The question is, well, then you could also say, well, maybe I just use a way smarter way of analyzing the point at the first place. So maybe I use the machine learning method to analyze these points. And then probably in this case, having a generative model in between who does this kind of oversampling is not necessary, because your very smart machine learning analysis tool already gets all the information the generative model also already picks up. And this is something you would probably need to test in practice, what's happening there. But then in also something, I'm kind of just repeating essentially what Gregor said yesterday.
You say it much more nicely, it's great.
Pardon?
You say it much better than I.
I'm not sure if I say it better, I say it in a different way. And sometimes it's helpful if different people say the same thing in different ways. And something he also said is like, yes, you can do this, but then the question is, what kind of analysis am I actually working on? So if I have a very particular analysis in mind and I'm only doing that, it's probably more sensible to just make your analysis, build the analysis in such a way that this already can extract all the information. But if you have a very broad way of, I don't know how many downstream tasks where you don't know what's going on, then you better say, okay, well, maybe then I use a generative model, which does the job for me. So I do the classical oversampling, and all the other tools, which I don't know what's going on, can still make use of my machine learning method, which kind of, prepared the data for them.
So we're going to go to the online questions next. So Igor.
Yes, could you please go back to slide 20 about matrix element method?
Sure.
One thing I wanted to note is we're probably missing a normalization for the efficiency, because if you integrate this probability, it will not integrate to 1. It will integrate to overall total efficiency, right?
Yes, but it's, I mean...
Okay, so that means if you want to stick it into a likelihood, it needs to be normalized. The second thing is, I think the schematic is a little bit too simplified, because what usually happens is that those probabilities x Rico, x hard, and efficiency x hard depend on things we call nuisance parameters or systematic uncertainties, right?
Yes.
So, for example, if you're going to, in a realistic case, do this efficient MC integration, your scheme is not going to depend only on the parameter of interest, it will also depend on nuisance parameters. And how would you handle this case? Because this quickly blows up to, like, you know, huge number of parameter values for which you need to construct your normalizing flow.
The short and honest answers, we didn't do this yet, because so far we just essentially tried to get the simplified problem already working, which was already quite hard. And a logical next step would obviously be twofold. One things, and actually something I'm working on currently on with CMS people, is getting these nuisance parameters in that thing. And yeah, so that's definitely work which needs to be done. It's not that we are ignorant about it, but it's we need to start somewhere. And even the simplified approach was not trivial. And of course, you like you're doing your studies, right? You know, not always start immediately with the most hardest and most realistic problem. You first break it down to simpler tasks, you solve them, and then you go on. And that's kind of what we do.
Okay, and we'll go to Nico next online.
Yes, hello. So yeah, thank you for the nice overview. I wanted to ask on slide 21, there you said that the Bayesian neural networks, they have this systematic uncertainty from training.
Yes.
And I was wondering, how do you estimate it? Is it simply by varying the weights on slide 17, or is there something more to it?
So what you essentially do is, once you have the sampling over your weights, this effectively means that when you're in the end of the day interested in the mean, which is the middle curve, you're sampling your weights effectively, I don't know, a couple of times, let's say 100 times. And this gives you out 100 predictions, and then you can calculate a mean and a standard deviation. The standard deviation of this is the uncertainty band.
Okay, okay, thank you.
And then, of course, something which is not in here, but is something you have to check is what you get out actually something which kind of looks Gaussian-like, so that you can actually make sense of calculating standard deviation.
Mm-hmm.
You can also calculate things like pull. So is the prediction minus the prediction divided by 2 times standard deviation, does it look like a normal distribution, things like that? So you need to make sure, is it well calibrated?
Mm-hmm.
This has been done, and this is correct. I'm just not showing you the plots here, but this is something you of course have to keep in mind. And if these things fail, you need to make sure that you either correct for that, or you kind of say, well, these uncertainties are underestimated, and yeah, you cannot approximate them better.
Okay, thanks.
And we're going to Kyle next.
Yeah, thanks for a nice talk. I just, on this particular point, I mean, that's probably too not a good thing for like this kind of post talk, but you know, the profile log likelihood ratio curve is kind of, you know, meant to already incorporate all the uncertainties. So, you know, putting uncertainties on the profile likelihood curve is kind of, you know, conceptually funky. And you know, what the meaning of the uncertainties from Bayesian neural networks means is also, it's a can of worms and too nuanced probably to try to deal with shortly. But, you know, I just wanted to call out that it's you know, it kind of indicates something, but it's hard to know how to interpret that exactly, or what you would do with that uncertainty band, or what like statistical statement would follow.
Yeah. Well, I would say how you really want to interpret, I'm not sure, but I would generally say you're right that in principle, this log likelihood should already be the optimal test statistic, as essentially that's what you want to say, and it should incorporate uncertainties. But it only is optimal test statistic in terms of statistical uncertainties, right? So if they're systematic, it's not necessarily.
Well, I mean, the profile likelihood ratio is meant to incorporate the uncertainties. You know, you would have like a log likelihood curve that would be much narrower if it didn't include profiling. Once you profile, it's wider. There's no statement about anything being optimal for either one, because it's not simple hypothesis testing, but there's kind of asymptotic statements. But I guess my point is just that normally you try to figure out how to incorporate your treatment of all of the uncertainties, you know, up until the point that you finally get to this number, some final number, which may be the profile likelihood or something else, where the uncertainties have been incorporated and you kind of have some kind of clear statistical statement. And if you then put like uncertainties on that, then it gets to be, it's like errors on errors, and it just starts to be conceptually confusing. But the whole thing is confusing. So like I said, it's not really it's a difficult conversation. It's like you can set aside an entire like session for that topic because it's so subtle.
What you don't see, because he's like just waving furiously as Tillman wants to say something to that. So maybe he can comment, because otherwise
Otherwise, I'm going to shut up.
Yeah, he's going to break down.
Hey, Kyle. I agree with you. The uncertainties are all in the likelihood ratio. What that error bar shows is the one uncertainty that's not in the likelihood, and that comes from training the network on the data. Well, I mean, these uncertainties which are related to the network training, as it says, like, what someone said. So these are basically like, uncertainties that come from approximating like the underlying function from and this is exactly what in that case the Bayesian networks should quantify.
Yeah, no, I mean, I guess I know that, but it's not really clear if that's do you call that an uncertainty or not, or is that just a choice, or like there's all
you can also call it some kind of whatever. Yeah.
The final question, so we don't lose too much about copy breaking.
Right. I wanted to quickly go back to philosophizing about Louis' favorite topic of amplification. So for me, I always thought this is related to the implicit inductive bias. So the neural network is making some assumptions. So in some sense, it is related that you have a deep neural network and not a shallow one. And also a bit what Baldy said this morning, why you don't have overfitting, right? So it is making some smart assumption, and it does an excellent job at any of the distributions we encounter in science, natural distributions.
That was more a comment than a question.
Yeah. And then the second one, quickly, laser, is this working sufficiently well already? This sounds like awesome for people in Atlas who all complain about weights on Monte Carlo simulation.
Yes and no. I mean, it works. The problem is, which I just kind of said in 2 sentences, is you have to pull these weights to a latent space. And then, of course, you need to sample. This effectively deforms your distribution in the latent space. And it's not necessarily efficient, depending on how large your weights are, to now sample from the deformed latent space. Because we use some MCMC, some Hamilton Monte Carlo, which is fast if the deformation is small, but of course, if the weights are large, then you essentially end up having this super slow, and then you're also not really gaining a lot.
We should thank the speakers again.
Copy will now be available for people who voted already on the posters. Seeing we finished a bit late, let's come back at 4:35, 5 minutes late.